Every time you tap an app, buy a coffee, or load a web page, invisible software systems are talking to each other. Welcome to this explainer where we're going to dive into exactly how these completely different systems manage to communicate. We use interconnected software every single day, usually without a second thought. But under the hood, making separate systems talk to each other is literally one of the most foundational challenges in all of computer science. Let's get into it.
Okay, let's start with a really simple human analogy. Picture two people standing in a room. If one person only speaks German and asks, "Wie viel Uhr ist es?" and the other person only speaks French and asks, "Quelle heure est-il?" how do they ask each other for the time without a translator? Well, they can't, right? Without a shared language or protocol, the message is just totally lost.
And that language barrier, it perfectly illustrates our core concept today, interoperability. It's basically a system's ability to effectively function and communicate with other distinct systems. When we build software today, we aren't just building standalone islands anymore. We're building interconnected components that absolutely must figure out a way to share information, exactly like those two people trying to agree on the time.
So here is our roadmap for today. We'll look at the interoperability problem itself, break down the logic, location, protocol framework, track its evolution to modern web APIs, look at the languages they speak, and finally, hit on the real-world economics of plugging it all together.
Part 1. The interoperability problem. Why is this such a big deal for engineers?
Well, software just doesn't exist in a vacuum. Think about the massive spectrum of interactions happening right this second. On a micro level, your software might just be trying to tell your operating system how to print a receipt to a local printer. But on a macro level, you're saving files to iCloud or OneDrive, which means communicating with massive remote servers. Sometimes developers are blending different programming languages, or even trying to hook up modern code with ancient legacy systems built in COBOL decades ago. In every single one of these scenarios, systems are constantly trying to bridge a gap so they can actually function together.
Part 2. Logic, Location, and Protocol. So how do we actually bridge that gap? We do it by using a universal three-part framework. It doesn't matter what the technology is, whether you're making a system call or hitting a web API, it all boils down to these three steps. First, you have the logic. That's the actual code that has to be written to handle the request. Second, the location. How do we find the external service? Usually that's an IP address or a web URL. And third, the protocol. This establishes the strict rules of communication so both sides actually understand the data being passed back and forth.
This brilliantly ties back to our earlier analogy, by the way. Asking for the time requires the logic of formulating the question in your head, the location of finding another person in the room to ask, and using a shared protocol like agreeing to speak French or German so the other person actually understands what you're asking them. Moving on to part 3, let's see how this framework evolved from older distributed tech to the modern web.
Before modern web services completely took over, there was Java Remote Method Invocation, or RMI. When Java launched in '95, distributed object computing was the absolute holy grail for enterprise systems. By 1997, RMI hit the scene, and it completely dominated enterprise development right up into the early 2000s. It was a huge leap forward, but as the internet evolved, RMI kind of fell out of favor. By 2014, key parts of it were deprecated, leaving it mostly as legacy tech today.
The journey of RMI is pretty incredible. It started as a revolutionary concept in '97, literally letting a Java object in one virtual machine command another object on a totally separate machine. But it hit a massive wall against web services in the early 2000s. Why? Because it basically only worked smoothly if both sides were running Java applications. As the industry shifted heavily toward cross-language communication and HTTP-based cloud microservices, RMI became this legacy tech that's maintained today primarily just to keep older systems running. If we compare legacy RMI to modern web APIs using our triad framework, the contrast is staggering. RMI was super locked down. The logic was tightly tied to Java interfaces, the location relied on a dedicated Java registry, and the protocol used these highly complex formats. But web APIs, they blew the doors wide open. Your logic can be written in literally any language using simple HTTP POST or GET requests. The location is just a standard web URL, and the protocol is universally readable, structured data.
Which brings us to part 4, speaking the same language. Let's look at what those modern data formats actually are.
Today, JSON, or JavaScript Object Notation, is the absolute de facto standard for data exchange. It's lightweight, it's highly readable, and it perfectly maps to modern JavaScript tools, like using the Fetch API's JSON method. Now, XML is still out there, usually parsed as plain text, and you'll see it heavily in enterprise or legacy setups. And when we need to send raw binaries over an API, like images or video, we encode that using base64 and process it using the blob method.
Speaking of the tools we use to pull all this data into your browser, there's been a massive evolution there too. Older code bases might still rely on XML HTTP request, which, hilariously, is an incredibly misleading name. It is not limited to XML at all. It can grab basically any data type. But even though it works perfectly fine over HTTPS, modern developers rely way more on the Fetch API. Fetch is just a much cleaner, more versatile way to make HTTP requests and handle the responses beautifully using those specific text, blob, and JSON methods we just mentioned.
All right, Part 5, Economics and Legal Implications. Let's pivot to the real-world reality check.
I love this quote because it really says it all. Utilizing a third-party web API essentially means that someone else is doing or has done something for you. Whether you're pulling weather data, verifying an IP address, or processing a payment, you are fundamentally relying on the fact that someone else wrote the code, maintained the server, and solved the problem for you. And frankly, they usually want to be paid for that.
This sets up a fascinating and sometimes dangerous economic dynamic that we can call the scaling trap. Look, using someone else's software is incredibly cheap or even totally free when you're tiny. A small hobby project might use a basic NeoCities API tier for practically nothing. But the absolute second your application starts scaling up and processing thousands or millions of requests, the paradigm shifts violently. Suddenly, you're hitting enterprise pricing tiers like AWS pricing, and you're forced to navigate some pretty strict legal liabilities around uptime and data sharing.
So as we wrap up this explainer, I want to leave you with a final, provocative thought. We've seen how elegant the triad of logic, location, and protocol is for making systems talk. We've seen how seamlessly modern web APIs and JSON bring it all together. But in a world completely reliant on interconnected APIs, when you sit down to build your next big project, who is really paying for the underlying logic, location, and protocol? Think about that the next time you effortlessly pull in a third-party service. Thanks for joining me on this deep dive into software interoperability.